and welcome to the webinar, Midas-Total Solution for Steady State and Transient General Flow Simulation by Faculty of Engineering and Built Environment of Massa University in collaboration with IMIKI. My name is Fabriha Ibnat, and I'm a engineering degree student in Massa University, and I will be serving as your moderator today. Today, we will be hearing a presentation from Mr. Kwa Chong Jin. Mr. Jin is the founder of Numit Engineering, and he started his first job as an industrial engineer and has had big experience history in handling a lot of significant projects, especially in the major field of computational fluid dynamic, CFD, and finite element analysis, along with a lot of other big achievements. Without further ado, I would like to welcome Mr. Jin, who will be speaking to us on Midas Total Solution for Steady State and Transient General Flow Simulation. All right, Mr. Jin, the floor is yours.
Okay, thank you very much, Fabriha. Good afternoon. Well, basically, you can call me just CJ. I'm broadcast directly from my office, Numi Engineering in Selangor, and I'll be presenting some case study about CFD, which is fall into a steady state analysis as well as transient analysis as well. So at the end of the presentation, I will show you another case study, which is on the HVAC application. All right. So basically, I have shared with my screen. Fabriha, can you double check whether you can see my screen?
1 second.
Yes.
Are you presenting right now?
Yes, I'm showing the PowerPoint right now.
Okay, now it's visible now.
Okay.
All right, thank you.
Okay, so I will start the a short presentation before I move into a demonstration of using the software called Midas. So basically, I'm from Numi Engineering, located in Selangor. We have been doing for simulation works and reselling our software for more than 10 years. We focus a lot in a lot of industry like automotive, aircraft. We have in medicals, we have general mechanicals, electronic semiconductors, and etc. So those industry basically are applicable of implementing our software in either finite element analysis or computational fluid dynamics. So today I'll be presenting to you about Midas total solution, which is on computational fluid dynamics. And at the same time, basically Midas has both capability as well. Instead of computational fluid dynamics, which is CFD, at the same environment, basically we do also for finite element analysis at the same time. So just a brief with our company, Numi Engineering. So we serve our engineering simulation for more than 10 years in R&D, which is research and development, as well as D&D for product design and development as well. We serve not only for industry application, but as well as the R&D's institute in Malaysia. We do serve in academic institute in Malaysia also. Besides focusing on CAE which is on engineering simulation for CFD and FEA, we also focus on lean manufacturing system like lean production system LPS for smart manufacturing. We provide engineering solution not only by reselling our software, but we also provide our services. We provide our training, we provide our support for the users in Malaysia as well as the Southeast Asia. So besides we are working deeply in engineering, we do have some branch of business which is fall into this finance products, and we also make some available of this e-store for e-commerce. A general introduction of our company, Numi Engineering. We have been working thoroughly with our client for more than 10 years, and we gather quite a number of clients as well from industry, which is for electronic or oil and gas application. We have several collaboration with university as well to work with them in their research and development. In-house, basically, we have several hardware, we have several licenses of conducting several simulations for our client. As you can see from here, the facility which include those software. At the same time, we also do our own in-house development as well, which is focusing on the customer relationship management system for database. We also develop electronic accounting management, and we also develop in-house our new software named electronic inventory management system. This is how we collaborate with our principals from all over the world, then bringing their technology into Malaysia for implementation as a solution for industry, as a solution for academic. We collaborate with the SimFlow for open form application, which is the open source CFD software. We collaborate with Siemens. We collaborate with Numeka. We collaborate with Midas in Korea. Numeka basically actually located in Brussels in Europe. We collaborate with Fraunhofer as well in Germany. Recently, we have collaborated with NCIS also, which is from US and India. So as a distributor, as a partner, technical partner in Malaysia, so we are not only distributing their software in terms of licenses, we are distributing their technologies for engineering solutions in this engineering design, engineering research and development as well. And you are seeing the slide that our client, okay, in Southeast Asia, for automotive application, for aerospace application, for construction and heavy equipment, for semiconductor, electronic and electrical as well, for general equipment and institute, for medical industry, and etc. So the software is not limited for a mechanical purpose. It's not limited for electronic purpose as well. So the software has been widely implemented in non-mechanical industry like these medicals, like semiconductors as well. In the past 10 years, we have worked closely with our local industry to develop and deliver the engineering services, and as well as the some benchmark with them. For example, like with MIC for shipbuilding using FEA, for oil and gas, for example, with JP Kenny. Okay, so we were working with the stress and strain simulation of offshore platform, and etc. Okay, so today I'll be demonstrating a short case study on elbow with the CFD applications. So first of all, I would like to start with my software. So we'll be using Midas and FX in this case to model and design the elbow flow, where we have different temperature gradients. We have different velocities inlet as well. So in this case study, basically what you try to observe is that we have some length of this elbow inlet coming from on the left hand, and from the bottom, and also from the right. All right. So at the end of the day, you'll be able to see how the flow behave due to the flow gradient and the temperature gradient. So basically, this is the software that I'm trying to demonstrate, which is named as Midas NFX. It has been developed in Korea, which has the capability of CFD, computational fluid dynamics, as well as the finite element analysis. So let's start with the new sheet. and we will model it in 2D environment with the unit system of meter in our sample case study. All right, so I'm not going to make some detailed drawing over here, but I'm just showing you that yes, it's capable of doing the modeling instead of using CATIA, SolidWorks, and others CAD software as well. So what I'm trying to do is I'm trying to import the model here with the model. All right, so the case study basically focusing on 2D environment. So instead of 3D, yes, you can do on 3D and you can do on 1D. It depends on the application that you have. So besides we going in detail about the case study, so I'm just introduced to you how the environment of Midas and FX will looks like. This is very user-friendly environment. So it has the modeling to model your CAD designs, all right? So you can import or export from somewhere else and to somewhere else with different file formats. So you can create your own CAD over this environment by creating the point or curve, and you can actually extrude to become a surface or become a solid in this case. So you can have a total solution of preparing your CAD model within the environment of Midas and X before you really step into running the simulation either for the CFD or for the FEA itself. So over this environment, basically, you can see that we are driven by the workflow, okay, represented by the window tabs from the left to the right? So these are the workflow, standard workflow that will be represented for your CFD workflow as well as the FEA workflow. So the idea is very simple to have a simple modeling. So either first of all, you will get your own existing CAD from somewhere else by importing into this software, or you can create inside this software. And of course, you're familiar with the finite elements, you're familiar with the CFD, so you have to create a mesh using the tools over here. For these two tabs, basically, we'll focus on the finite element analysis. All right, so whether you are doing on static or dynamic analysis, whether you are doing for steady state of heat transfer or transient heat transfer, so you'll be focusing by using these two tabs. As for today's, we'll be focusing on CFD, which will be using like inlet boundary conditions, outlet boundary condition, and as well as the wall. Okay, so on the left, we have 3-bar. Okay, so this is where your CAD model is being saved. All right, so all your information of the setup will be appears over the left 3 bars. Okay, so we can have a different setting as well for the preferred setting, like the color of your windows. And you can play around with the different backgrounds. You can play around with the different colors, and you can have your own preferred language as well in this case. All right, so let's focus on the case study or demonstration today. So we're gonna have one inlet over here. Basically, the fluids that is going to flow within the elbow is actually a water. So we'll be create a water base from the library. Within the library, we have several liquids available. And in our case study, we'll be choosing the fresh water. So all the mechanical fluids properties will be displayed over here. And okay. And you may notice that the fresh water will be called out and will be displayed in your 3 bars. So we are going to apply the fresh water over the elbow by using a 2D properties. So we just go to CFD 2D and choose for the fresh water. And we should be able to create the mesh in 2D. All right, so this is the mesh generation. Using the autoface, and you have a several option to implement the different type of mesh, different type of method of generating the mesh. So in this case, I'm be preferring using the autoface. This is the size of the mesh that you're going to create in the unit of meter over here. Let's say if I would like to set the size of the mesh or the element into the unit of mm, so I'll be having 57, for example. All right, so let's preview the nodes and apply. So this is the mesh, this is the auto mesh created, right? So let's say if you're not satisfied with the mesh created, let's undo and let's put a little bit lower, let's say 40. And we will try to apply. Yes, you have to select the object as well in this case. So you're gonna get a smaller size of the elements, right? So I will go directly with about 10 perhaps, and you will get a smaller cell size compared to the previous setup, right? So how do you decide what type of cell size? Okay, what is the cell size that is appropriate in your CFD analysis? So this is something that you will not know at the beginning of the case study. So you will have to plug from sky. All right. So you have to, based on your experience, how actually you can decide what is the size of the mesh that you need to have. All right. So then you have to loop, you have to do a simulation, the first round simulation, and check with the result and check with your to validate your experimental result. So whether the setup of the mesh size or the boundary condition are actually suitable for your simulation. All right. So at the beginning, we will not know what will be the best value. So we just plug from sky based on our experience. So we just put it into the simulation first. Let's say I will prefer to use this mesh. Okay, so I'll just proceed with this mesh. And the next thing to do is very simple. So we have to know what are the boundary conditions to determine. So in our case, we have the wall. Sorry. So we have the wall of the pipe itself. We have the inlet section over here. And we have the outlet section. So now we'll be doing a different case study compared to our PowerPoint, where we have an extra 2 inlets, right? So I'll just show you the workflow, then we will add on with the next inlets. So let's go to the boundary condition 3 bars, and let's go to CFD. Let's choose the inlet. I'll select the edge as an inlet. In this case, my velocity is millimeter per second. I'll switch my unit to meter, because in my PowerPoint or my presentation, I know that is 0.1 meter per second. So I don't want to use my calculator, recalculate back from the meter per second to millimeter per second. So I will just use the value of 0.1 and okay. So you will be seeing a representative of the inlets by the sphere over here, and the information is kept into the 3 bar. So this is the first boundary condition, and I'm going to do it on the outlet. Okay, so I'm going to select the edge as well, and this is a gauge pressure, so I put it pressure as a 0. Then you should have the outlet, and in this case we're going to have wall. So all the tubes over here are selected in order to represent and as a wall, and we will tell the CFD software this is to be the wall. All right. So in addition, we have additional inlets, which is the temperature. All right. So this is the temperature we are going to impose at the inlet as well. So what I'm going to do is I'm going to just to click on the temperature and select again at the inlet edge and apply the temperature of 36.85, for instance, in this case 30 as a degree Celsius. So we are going to have all the parameter set up over here. So first of all, I would like to do a steady state analysis, and I'm going to the analysis and result, and just click here. I'll create a steady state CFD. And of course, I have to do something before I run the simulation. So I just need to make sure that all the setup are correct. For instance, like I'm using the mesh that I created earlier. I'm using the boundary creation I created earlier as well. And I need to do some setup in this case because in the physics flow, we're going to have fluid flow, and we will have also the fluid of heat transfer. All right. Then the second and the last thing, I have to tell the software that what is the initial condition of the environment. For instance, like what is the initial temperature of the fluids? What is the initial of the velocity of the fluids? So at the initial condition, the temperature is 28 degrees, for instance. So we are not doing for solid temperature, but we are doing only for fluid temperature in this case. We maintain the pressures, everything to be 0. Okay, and okay. So of course, we have to save the project first before we can actually run. And we should be able to run the simulation right now. All right, so this is what we are running, so-called the simulation. All right, so what we are trying to monitor here, this is the norm, or this is the residual, or we call it as a truncation error, because in the finite element or computational fluid dynamic finite volume, we are actually approaching our partial differential equation into a finite differencing. And when we are doing the finite differentiating, definitely we have a so-called some error. So we call it as a truncation error. So in this case, we call it as norm or residuals basically, right? So before I proceed further to explain about how the residuals works and how actually you can monitor the residuals. So I just save and stop for a moment. What a CFD user would do usually is, we know that this is the inlet and this is outlet, and we would like to monitor extra parameter, all right, at near to the outlet usually. So we will have to make sure that the velocity are so-called converge, the pressure are converge. In this case, because we include already the temperature or the energy equation, so we have to make sure that those information are really converge into the CFD solution. So we can place any sensors at any point. So usually I prefer to put it somewhere away from the outlet. So this is the sensor, and this sensor can be viewed over here. These are all the sensors I have selected at that particular point. Then let's rerun. Okay, so beside you are seeing the residue or the errors, okay, we are seeing the real value of the velocity itself. We have 0.1 meter per second, if you recall. We have pressure, which is the gauge pressure at 0 Pascal. And we also have the temperature. All right. So let's go back to the norm graph. Make sure that all the residues or the error actually belongs to or below 0, right? So the error should be 0.1 or 0.01 or 0.001, all right? So in this case, we have an error for pressure, which drop into 0.0001, which is to the power of -4, to the power of -5, and etc. All right. So this is the first thing you have to ensure. Make sure that all the residues or the norms fall below 0. And the second part that you will need to notify is that the behavior or the pattern of the flow of the residue itself. So make sure that there is no lot of fluctuation, like for example, like this one. So we may have to wait for the completion of the iteration, which we set at 1000 iteration in that case. And let's look at the other quantity, for example, like the velocity. So near to the outlet of the velocity, it becomes a straight line, which means a constant velocity has arrived. And let's look for the pressure. At the particular point, the pressure becomes a constant value as well. So it means that the velocity and the pressure are converged, and the temperature are converged as well. All right, so we have done our simulation, and let's look back the residues or the norms. So it's still below zeros, and you have a straight line pattern, so it looks good in this case. It looks promising. And let's go back to our model. So at the last time step, you should be able to see how the flow looks like. All right. So in this case, you refer to the legend on the right. The blue represent the lower range of the velocity. The upper represent the highest range of the velocity, and you may able to see the pressure as well, the pressure distribution, and also the temperature distribution. So it's not much difference in the case. Okay, so the second part is we are going to do a transient simulation. Okay, so which is before it reaching to a steady state. So what is actually happening in the transient simulation? So usually in heat transfer analysis, we'll do a transient simulation rather than a steady state simulation. So let's go to create another new case study of transient CFD, and make sure that I have selected the mesh and also the boundary condition. Let's check my setting. Okay, so I'll just put any value of number of iteration instead of 1000. I put it at 5000. So as I mentioned, that we were not able to know what is the number of steps, all right, for the iteration. So if you guys exposed to FEA or CFD before, I'm sure that you understand what is the number of step. So number of step is very, very important in the transience mode instead of steady mode, right? So in transience, you have to determine what is the number of step required and what is the number of delta t, which is the time increment, okay, you require. So we put everything to be default without changing anything. So unless we want to go for accuracy, then we will have to compare with the experimental study. Then we should be able to change those value accordingly. So how to change the value in a appropriate manner based on the training or based on your experience that you're going to have. And of course, don't forget to set up the fluid temperature of 8 degree. Remember to save, and you'll be able to run. Okay, so this is in transient, so which means that the time step is very important, and what you are seeing, the time step is actually the physical time step, how the flow starting from 0 second up to a time final second, right? Also how the heat transfer starting from the temperature of inlet distributing all over the region of the elbow pipe to up to the outlet as well. Right, so the same idea as well. So we're monitoring how the norms or the residuals or truncation error behave. So it looks like very steady at the end of the simulation. We will check the quantity of the velocity. It looks nice. The pressure and the temperature as well. All right, so it seems that everything goes well. So If I stop over here, it doesn't matter. All right, so let's see the total velocity. In this case, since that we are solving every delta t or every time steps, all right, so in terms of the velocity or the momentum itself, or we solve the temperature. Okay, so you should be able to see a little bit of how the flow behave in the transience mode. Okay, so not much difference over here since that the flow is quite steady. So we will be doing some modification in order to inject two more inlet now. So we'll go back in the design mode, and what I'm going to do is I'm going to import the two inlet 1 and inlet 2. Okay, so you'll be seeing these two extra inlets. So we have this curve, we have this surface. And let's switch off my mask. Okay, so what I'm going to do over here is I'm going to modify some model so that I will merge these two inlet into the same environment. So no, I cannot do that yet. What I will need to do is I have to create an extra or additional edge over here. So I create an additional edge so that I can remodel over here. All right. So let's make. Then I should be able to delete the curve. Put something like that. And be able to create another new model and rename this elbow to inlets. Okay, so I have two model. The first model, which I conducted the steady state analysis and transient analysis by using this mesh. And now I created an additional model, which I will going to inject additional inlet into this area and this area as well. I'm going to create the mesh for this second model. So in my case, I prefer to use millimeter, and perhaps I will try with 10 and see if the mesh looks nice. Well, the mesh is not sufficient basically, but this is just for distribution demonstration purpose. And in the real world case study, basically we have to take into the effect of the viscous flow. So we have to build more mesh near to the solid wall in that case. And how do we do that? So we have to control, layer control, and we should be able to create more mesh near to the solid wall. All right, so this is due to the layer of boundary condition due to the turbulence flow. Right, so just to keep it simple and easy, so we will accept this as the mesh, and the mesh we are going to use is elbow underscore 2 underscore inlets. So we'll be doing the same things as well in this case for line boundary conditions. First of all, we'll be modify the inlets into the meter. And what I'm trying to do is I'm going to add additional edges here, because in this case, we're going to have two models, the elbow and the elbow underscore 2 and the inlet. So I don't want to, lose my previous settings. So what I am going to do is just edit Okay, and you may see that selected one object, so which refer to the previous model, and I'm going to select another object, which is two object, including the current model, right, as a inlet. And I'm going to do it the same as well for the outlet. And I need to make sure that selected two object is being displayed. Same goes to the wall. So I have this wall. I have this wall. Okay. I have also this wall, the new wall. And let's press OK. And same goes with the temperature inlet, the first inlet. All right. So let's look at the, just verify that we have created a right location of the boundary conditions. Let's unselect the mesh, then we'll be able to see the model here. Let's put it into shading. And let's check the inlet. Yes, and we have the outlet. We have the wall. So we are missing one. Okay, so we'll be adding in. And we also have the temperature at the inlet. Okay, so we're gonna have two extra inlet in this case. We go to CFD, the inlet. So this inlet will be 0.4 meter per second. Right? And this inlet is also 0.4 meter per second. So we have one inlet and two additional inlet. Well, actually, we can rename it as inlet 1, perhaps, and inlet 2. So the original inlet will be 0. Okay, so it's easy for you to identify in this case. So we have one inlet, two inlet, and three inlet. And we're going to have a different temperature as well in this case. So we're going to select the edge over here, or the inlet edge. So in this case, we have 66.85. 66.85. And okay. And we can do the same thing as well. Inlet 1. This is belongs to original inlet. And we're going to have another temperature on the other range over here. Let's refer back 72.5. And this is okay. So we are done with the boundary condition with an additional of two inlets, an additional of two temperatures, and we have made sure that the wall are correct. So we'll be using the same boundary condition again for a second model of simulation. All right. So what I'm going to do over here is I'm going to copy a steady state from the previous case study, and I'm going to rename this one as two inlets. Why is to be three inlets, but there is the injection of the temperature referring to. So this is the two inlet, right? So you can make any name, preferred name that you want. So make sure that the new mesh will be selected. The old mesh will be deselected. Okay, so it doesn't matter if you select every boundary conditions, as long as you select the right mesh, that will be fine. All right, so let's save and let's solve. Then before we do that, of course, a new mesh has been created, and I will need to monitor the quantity, the physics quantity, and let's save and run it. Okay, so we will monitors how the norms goes, the velocity, physics parameter, the physics quantity of pressures, as well as the temperature. So you may see the temperature is rising up, while basically it is not reaching to any steady state yet, but this is rising up. So in the meanwhile, while waiting for the completion of simulation, we can actually reload the result to see how suppose it looks like, right? So we have quite an obvious result after adding two additional inlet. This is in terms of the velocity. This is in terms of the temperature distribution. Okay, so let's check. Yes, the temperature is rising up. It's not converged to a certain value yet. It's not a constant value, and etc. Okay, so I was save and stop for a moment, then I should be able to show you the transience setup also. Okay, so what I'm going to do is I'm going to copy the previous case study like what I'm doing for the steady state, and I'll go for edits, saying that this is the inlets of two inlets. For example, make sure that I have selected the right mesh, and make sure that the fluids there, the initial condition has been set up accordingly. Then I should be able to run a transience simulation. So let's check with the norms again. Okay, so what happen if your norms go above zero? So means that it diverge. All right, you should not proceed. You should not continue with your simulation. You have to stop. You have to check what is actually happening. All right, so if all the norms below zero, so you are safe. All right, and the second stage or the second level that you have to ensure again is that make sure that the fluctuation of the graph, all right, is not so obvious like what you're seeing at the initial point. So the norm basically are fluctuated until a certain point becomes a straight line. So it means that it converges at a very nice and smooth environment. Let's check again with the physical quantity of velocity, the pressure, and the temperature as well, right? So it seems to be converged nicely, and I should be able to save. And let's see the transience simulations. For instance, like velocities. So you should be able to play the animation as well. Okay, so this is how you're going to achieve a transience simulations. It looks like similar like steady state analysis, but the difference is that you have to specify your time step and the number of iteration correctly, right? So in steady state, usually we don't deal with a lot of the number of time steps, so it doesn't matter. The solver or the software basically will decide to you what is the appropriate time step. And you are looking into how the heat or the temperature are distributing throughout all the region of the pipe elbow. Okay, so I'm not sure if I will get any Q&A for the moment before I proceed to the another case, which is just demonstration on how you actually can achieve with CFD method for the HVAC analysis. So in this case, Pabriha, can I proceed with the next, or do you have any Q&A from the students?
There are no questions so far in the live chat, so I think we can proceed.
Okay, no problem. So since that there is no response on the Q&A, so I will show you another case. right? But it's not in the demonstration mode, but the workflow will be similar than what you were seeing for this elbow pipe. In Midas NFX, you can deal with multi-sheet. Okay. This is hot fluid. Just a moment. Let's see. So multi-sheet means, or multi-project means you can open a several project throughout the same environment, and you can work it out at the same times. All right. So this is a room. Okay, let's see in the model itself. Yes, this is a room. Oops, sorry. Okay, so what I'm going to show you, this is going to be a room with a few windows over here. We are going to place an artificial humans. Oh, this is not the one. A simplified humans over here. Okay, in order to generate the heat flux or the heat source. Okay, so the idea and the objective of the case study is that we will need to design the heating and ventilation condition in this environment by so-called the natural convection, as well as by the nanopipe cooling. All right. So just a moment, if you can see well about the real. Okay, so I just need to make sure that, oh yes, just a moment. Display mode, line only. Okay, so you will see better in this case. All right, so we have two simplified human being. All right, so we don't use the real human being usually, because with the real human being, basically you will create a lot of meshes, and you will define a lot of error in that case. So we will use something to represent, unless it is so critical that you have to put in a real human being within the simulation. For instance, like a crash test analysis. Right, so in each of the body, on each of the surface, you have different normal direction. Then you have to include the real human being model within the software. Right, so in this case, basically, this is a real case study. This is a commercial case study. So we implement only a simple human cylinder in this case, and within the room itself, we have the pipe that is flowing with the fluids, with the liquid at the temperature of 6 degrees Celsius. Right, we have the fins. Right, so those pipes basically are built inside the wall. Right, it has to build inside the wall. In this case study, basically it built at the top of the room. All right, so we will initiate an simulation for the natural convection. So in this case, basically we're gonna have two fluids. Right, we're gonna have one fluid that is flowing inside the pipe, the cold fluid. We call it as the cold fluids, and we have the hot fluids within the room itself. And the heat is generated by the human cylinder. Okay, so in this case, I'm going to show you the human cylinder. Oops, this is the heat flux. Moment, please. This is the hot fluids. This is the outlet temperature, or the outlet pressures. And we're going to have this, the heat flux itself. Yes, because, okay, so we will include this one. Okay, so let's check with the boundary condition in this case. So we have the heat flux is actually coming from the windows. we're gonna have this flow, the cold fluids in, which I mentioned is at the certain velocity, and we also have a temperature at the same inlet as well. If you look into here, yeah, so the temperature is applied over here, so you can see very well. We have the outlet. So this case study is involving two different type of fluids, okay, the hot air and the cold air itself, right? So initially we have to prepare the materials or the fluids. We have the air as a fluids, the water as the fluid also, all right? The water is the cold fluid basically. So we do have a human being as well, because these materials is embedded in the human being with the heat source of this. All right. So meaning that in that case, we have two different heat generations. So one heat generation is coming from the windows of the room, and another heat generation is coming from the heat source of the human cylinder. So let's see back the setup. We're going to have radiation. Okay, so in this case, we're gonna have a radiation, heat radiation coming from the human, and also the heat radiation coming from the wall of the room. All right, so this is a little bit complicated case study, which we involve quite a number of physics phenomena. And of course, you may want to see how the mesh is created. Okay, so the mesh has been created independently, and let's say for example the hot fluid, this is the room, right? The room only, we have the cold pipe or the fluid itself. This is the fluids, and we have the pipe also, okay, for thin heat transfer analysis. And we have the human cylinder, and the all the mesh has been merged in terms of the nodes, and we should be able to run the analysis as much as possible. So there are a few steps which I do not show you. In this type of case study, basically we perform some node merging and all those things. So this is considered some a little bit one simulation, but it's applicable in the HVACs, usually in the HVACs. And perhaps you would like to see the results. We have a transient result, and like what I say, usually we prefer to do a transient simulation. Okay, so let's look at only the hot fluids. Show only. Oops, sorry. Show only. Let's make some cutting. Don't show the edge. Let's align. Oops, sorry. And you should be able to notice how the temperature are distributed. You can see that the cold air is coming from the top, all right? So the hot air is reaching about 38 degrees Celsius. The cold air is about 16 degrees Celsius. So how the cold air is supposed to cool down the environment effectively, okay, from the point of view of natural heat convection in this case. So this is one of the type of heating and ventilation application in the real world, in the real industry, basically. So we are actually building all the cold pipe on the wall. Okay, so to eliminate the usage of the air conditioning system, just to make sure that the green environment is over there, and to achieve our final temperature of the room itself. Okay, so I guess that is all about my demonstration and presentation about how Midas NFX can actually provide you a total solution, not in only in CFD, but as well as in the FEA also to do quite a number of simulation. Yep. So, Ms. Fabriha, so that is for the presentation right now.
Okay. We have come to an end to the presentation. Thank you so much, Mr. Jean, for addressing this interesting topic. And thanks to our audience for active participation. Hopefully, the presentation was beneficial for everyone. And on behalf of Masa Aimiki, I would like to thank you for joining us today. And thank you for your time and patience.
Okay, thank you very much.
If anyone has any questions, they can drop the questions in the live chat.